Before we define Laplace transform, let us first review the definition of an improper integral. The improper integral of a function f of t from a real number a to infinity is defined as a limit where the infinity is replaced by a number b, where b goes to infinity. If the limit exists, the improper integral is called convergent. If it does not exist, it is divergent. The Laplace transform is defined for a piecewise continuous function f of t, defined for t greater or equal to 0 using an improper integral, where it is integrated with the function itself with e to the negative s of t. If the integral converges, then the Laplace transform for the function f of t exists. Notation-wise, we use the lowercase for the original function in the time domain, and we use uppercase for the Laplace transform function, so we call it in the S domain or the Laplace domain. Before we go into the details of calculating and evaluating Laplace transform, I want to first motivate the use of Laplace transform for solving complicated differential equations. Usually, for the system, we are often defined using the function f, which is in the time domain. That is described by a difficult ordinary differential equation to solve. And we want to solve that ordinary differential equation to obtain a solution of the ODE. However, this is often difficult to do. Well, if we use Laplace transform, we can go from the time domain to the Laplace domain. What that does is it converts a difficult ordinary equation to an easy algebraic problem. And solving the algebraic problem is often easy. Finally, we go from the solution of the algebraic equation back to the solution of ordinary differential equation using inverse Laplace transform. And this is like what we have learned in thermodynamics, where a difficult path is often hard to achieve. Then we seek an alternative path. And the alternative path we're using here is the Laplace transform. Now let's dive in. How do we actually evaluate Laplace transform? By looking at the simplest example of a constant, where f of t equals to c. We first recall that the definition of Laplace transform of a general function is integrate from 0 to infinity of the function itself multiplied by e to the negative st dt. In this case, we're evaluating the Laplace transform of c, constant. So we multiply c by e to the negative st and integrate. And because c is a constant, we can pull it out. And we're just integrating e to the negative s of t. We can do a u substitution where u equals to negative s of t, and so du equals to negative s dt. And then remember, we need to change the bound, so u of infinity equals to negative s infinity, which is negative infinity, and u of 0 is negative s times 0 is 0. So we can substitute those in. We have the integral from 0 to negative infinity of e to the u du. But notice that dt equals to du divided by negative s, so we substitute that as divided by negative s. Okay. Now we view s as a constant, so s can be taken out. So we're integrating e to the u from 0 to negative infinity. And to expand that, we have e to the negative infinity minus e to the 0. And e to the negative infinity is going to 0. So that goes out. and e to the 0 is 1. So finally we have the Laplace transform of constant is the constant times 1 over s. So for example, if I have the constant is 1, so here c equals to 1, I have the Laplace transform of 1 is 1 over s. If c equals to negative 2, then the Laplace transform of negative 2 is negative 2 over s. Now let's look at a slightly more complicated example of the Laplace transform of a linear function t. So by its definition, integrate from 0 to infinity of the original function t multiplied by e to the negative s of t dt. Because we have two functions multiplied by each other in the integrand, we need to use integration by parts. So let u equals to t and dv equals to e to the negative s of t. We have du equals to dt and v equals to integrate e to the negative s of t. And that is what we just did, which is 1 over s negative e to the negative s of t. If you're unsure of this result, you can take the derivative. So negative s goes down and it cancels out. Now we plug it in. We have the original function u equals to t multiplied by v, which is negative 1 over s e to the negative s of t. Evaluate it at 0 to infinity, minus the integral of v, which is negative 1 over s e negative s of t, du, which is dt, and then evaluate that. We first plug in infinity, but note that we have t and e to the negative s of t. The exponential decay decays faster than linear function, so the first term goes to 0. The second term, if we plug in 0 to t, that's also 0. Minus goes to plus. And then s of t is a constant, so we take it out and integrate 0 to infinity of e to the negative s of t dt. And we have the integral of e to the negative s of t is negative 1 over s e to the negative s of t as before. Then from 0 to infinity. Take out the 1 over s. We have e to the negative s times infinity minus e to the negative s times 0. E to the negative infinity is 0, and e to the 0 is 1. So the negative signs cancel. We have the Laplace transform of a linear function t is 1 over s squared. Now let's look at the Laplace transform of an exponential function. So here we have Laplace transform of e to the negative 3 of t. By definition, integrate from 0 to infinity of the original function multiplied by e to the negative s of t dt. We can merge them together using the property of exponents. And we can also extract the t out. So we have negative s plus 3t. We can use u substitution where u equals to negative s plus 3 of t. So du equals to negative s plus 3 dt. And dt is du divided by negative s plus 3. I won't change the bound yet. I'll leave the bound in the variable t, and that will serve us some use later. So I have e to the negative, e to the u, because negative is included, and du divided by negative s plus 3. And negative s plus 3 is a constant that we can take out and evaluate the integral. We have e to the u from t equals to 0, t equals to infinity. And to evaluate that, I want to change u back to t. So I have u equals to negative s plus 3 t infinity 0 to infinity. And then negative 1 over s plus 3, I have substitute an infinity in e to the negative s plus 3 infinity minus e to the s plus 3 negative 0. We have negative e to the negative infinity, which goes to 0, and e to the 0, which is 1. And there's a negative sign here, so we have plus s plus 3 is the Laplace transform of the exponential function. But note that here we conclude that e to the negative infinity goes to 0 is because it is an exponential decay. So the exponent has to be less than 0, has to be negative. So the exponent, which is negative s plus 3 t, must be smaller than 0. And this gives us a constraint on s. So solve for s, we have s plus 3 t goes to the right side, and the negative goes to the right side, which changes the sign. So s must be greater than minus 3. And this is the constraint on the Laplace transform we had. And similarly, we can evaluate the Laplace transform of the positive exponential function. To do that, we also use its definition. And then we can group them. So we have negative s minus 6 t dt. So also do a u substitution. du equals to constant dt, and therefore dt equals to du minus s minus 6. I'll still leave the bounds as t. So e to the u du negative s minus 6. Okay, and 1 over minus x minus 6 is a constant that I can take out, and then I do the integral of e to the u, which is also e to the u, for the bounds t equals to 0 and t equals to infinity. And I change the u back so that it is e to the negative s minus 6 t from 0 to infinity. Similarly, I've evaluated, it gives me e to the something minus infinity minus e to the 0. So the negative 0, this is 1. So negative cancels out. So I have 1 over s minus 6 is my final result. But still note that the exponent has to be smaller than 0 in order to make that goes to 0. So minus s minus 6 t must also be smaller than 0. Then we can solve for that. So s must be greater than 6 is the constraint on the Laplace transform of e to the 6t. Laplace transform of sinusoidal functions are common because there are a lot of sinusoidal response for control. So let's look at an example of the Laplace transform of sine of 2t. So by definition, we integrate it by multiplying it with e to the negative s of t dt. Then we again use integration by parts. So du equals to cosine of 2t, and then chain rule, dt. V equals to negative 1 over s, e to the negative st. And these are occurring very commonly, so we should remember that. And then we integrate from 0 to, we substitute u, which is sine of 2t, multiplied by v, which is negative 1 over s, e to the negative s of t, from 0 to infinity, minus the integral of v, which is minus 1 over s, e to the negative s of t, times du, which is 2 cosine 2t dt. Organize that. Sine of infinity is oscillatory, but e to the negative infinity is 0. So it's 0 minus sine of 0 is also 0. There are two minuses, so that becomes a plus. The integral of 0 to infinity, 1 over s is a constant, and 2 is also a constant, taking them out. So integral of e to the negative s of t cosine 2 of t dt. Now we again have two things multiplied by each other, so do another integration by parts. So u equals to cosine of 2t, dv equals to e to the negative s of t. And this we have already solved for. And du equals to sine of 2t, and then chain rule gives us 2 dt. Okay, and then we substitute things back in again. So 2 over s is at the front, and then u is cosine of 2t, v is negative 1 over s, e to the negative s, and then minus the integral of v du, which is negative 2 sine of 2t dt, and then bracket. Okay, let's reorganize this. Cosine of infinity is oscillatory, but e to the negative infinity is 0. And then cosine of 0 is 1. Minus is plus, 1 over s, e to the 0 is also 1. Then minus the integral of minus 1 plus 1 over s, and there is another minus, so that becomes a minus 2 e to the negative st sine of 2t dt, bracket. Let's reorganize everything. So 2 over s multiplied by 1 over s minus 2 over s, the integral. And this integral looks familiar. This is exactly where we started. So this integral is the Laplace transform of sine of 2t. So we can write it out as, and multiply the 2s out, so 2 over s squared minus 4 over s squared equals to the multiplied by the Laplace transform of sine of 2t. Okay, and because we have the Laplace transform at both sides, we can isolate that and solve for it. So we have, if I plus this to the left, I have 1 plus 4 over s squared. The Laplace transform equals to 2 over s squared. So that gives us that the Laplace transform of sine of 2t equals to 2 over s squared divided by 1 plus 4 over s squared. Then to simplify this, multiply by 1, a common trick, so top and bottom multiply by s squared. I have changed nothing. And then at the top I have 2. At the bottom I have s squared plus 4. and this is the Laplace transform of sine of 2t. And in the derivation, we have constraint on s. If we just look at the result, we would say that, okay, s squared plus 4 must be greater than 1, which is always true for all the s's. But if we look at the derivation, we have places where we have 1 over s. So that gives us that s cannot be 0. And there are also places we use that e to the negative s of t evaluated at infinity goes to 0. And this tells us that negative s of t must be smaller than 0. Otherwise, that identity cannot be true. So s must also be smaller than 0. So combining s can be everything, s cannot be 0, and s is smaller than 0, we choose that the constraint for the Laplace transform is s is smaller than 0. Remember that in the definition of Laplace transform, we said that the function can be piecewise continuous. In this case, we want to evaluate a function where it is 0 from 0 to 3, but 2 from 3 on. So we plot it over t, f of t, from 0 to 3, it is 0. It is including 0, but not including 3. But at 3, we have, it is 2 and goes to infinity. Okay, we want to evaluate the Laplace transform of that. So the Laplace transform of this piecewise function, again, we do use the definition by integrating 0 to infinity of 0 when t is in 0 to 3, and 2 when t is 3 to infinity dt. E to the, remember we have to multiply by e to the negative s of t dt. Okay, but now how do we integrate that? What we can do is to break it down, to integrate first part and then integrate the second part and add them together. This is because if we integrate from a to c, then it is equal to, say this is a, b, and c, then it is equal to integrate from a to b dt plus from b to c dt. We can use that here. So we can integrate from 0 to 3 and then integrate from 3 to infinity. What's inside is first the original function 0 multiplied by e to the negative s of t, then into 3 to infinity part is 2 e to the negative s of t. And here we have, because this is 0, we're integrating nothing, so it's also 0. So at the second part, 2 is a constant that we can take out, and then integrate e to the negative s of t, which is negative 1 over s, e to the negative s of t from 3 to infinity. And then negative 1 over s is a constant, so we can take it out. E to the negative infinity is 0, and then minus e to the negative s of 3s. And then reorganize this, the negative sign cancels out, and we have finally 2 over s e to the negative 3s. And then as we look for constraints of s, if we look at the example, the final result, s can be anything. But in the derivation, we see that there are instances where we use 1 over s, so that s cannot be 0. And there are also places we use e to the negative s, evaluated at infinity goes to 0. So that gives us negative s of t is smaller than 0. So s must be greater than 0. So that is the constraint of the Laplace transform of this piecewise function. So why do we bother to have Laplace transform? Laplace transform are easy to work with because they are linear. So let's review what is linear. So a linear combination can be a multiplication of terms by a constant and or addition of terms. For example, say we have constant of c and d and terms of f of t and g of t. Then multiplication of terms by a constant means that we can have c of f of t. It is a linear combination. D of f of t is a linear combination. C of g of t is a linear combination, or D of g of t. These are all examples of linear combinations. And for addition of terms, I can have f of t plus g of t. That is a linear combination. And if I use the AND condition, then I can have c of f of t plus g of t can be an example. Maybe c f of t plus d of gt, that can be an example. The most general example for this combination would be c of f of t plus d of gt for two constants and two terms. We can also generalize that for n terms, where we have c1 f1 plus c2 f2 plus 2 cn of fn, and this can be written in the form of summation of c of I, f of I. This is the most general form of linear combinations. And linearity means that when the transform of a linear combination, for example, I have here a transform denoted by t of a linear combination in the most general form for two terms, equals to the linear combination of the transforms. So I have individual transforms for f and transform for g, and the constants can be taken out. And if this condition is satisfied, then the operation or the transform is called linear. We have already seen this kind of linearity before, where, for example, we have derivatives. So d dx of a constant alpha, f of x plus beta g of x. We can break them down into d dx of alpha f plus d dx of beta g using the addition rule. And then the constant can also be taken out. So I take out the constant now, and if we compare these two terms, it satisfies the linearity condition. So we say that derivative is linear, is a linear transform. Similarly, we'll also have integrals where we can integrate a linear combination dx, and we can take the constant out and then integrate each function separately. And we say that the integral, and in this case is indefinite, integral is linear. And another similar example is a definite integral, where we have, if we integrate from a to b of the linear combination, and we still can take out the constant and integrate each thing individually. And we say that the definite integral is linear. And why do I say Laplace transform is linear? It is because, if we recall, the Laplace transform of a function is defined as the improper integral 0 to infinity of f of t times e to the negative s of t dt. Right? And that is very similar to a definite integral. and we shall prove that. So now let's demonstrate that Laplace transform is linear using the definition of Laplace transform. So first let's set up a Laplace transform for alpha f of t plus beta g of t. And we use the definition of Laplace transform. So we have the Laplace transform of 0 to infinity of the original function, which is alpha f of t plus beta g of t, multiplied by e to the negative st dt. Okay, and then if I multiply things out, I have alpha f of t e negative s of t dt. Let's don't jump ahead of ourselves. Let's have plus beta g of t e to the negative st dt. And I can use the definite integral addition rule to separate these things out. So alpha f of t e negative s of t dt plus the other half. This is using the addition rule of definite integrals. Then I recognize that alpha and beta are constants, so I can take them out. And now I can see that this integral is exactly the Laplace transform of f of t. And this integral is exactly the Laplace transform of g of t. And the linearity condition is satisfied. So, and this is very important when we're evaluating more complex Laplace transforms. So alpha Laplace transform of f of t plus beta Laplace transform of g of t. Now let's look at a simple example of using the linearity of Laplace transform, and this is shown again here. And then where we can also write it in this form, where the Laplace transform of the time domain function can be written as the capitalized form using the notation introduced before. So the linearity condition can be used to evaluate additions. So we can break it down into the Laplace transform of 1 plus the Laplace transform of 5 of t. And then we can also take out the constant, so 5 Laplace transform of t. What is the Laplace transform of 1? The Laplace transform of 1 proven before is 1 over s. And the Laplace transform of t was also proven before as 1 over s squared. And now we have solved the Laplace transform for addition of terms.